My name is Michael Doan. I'm in third year aerospace engineering major. This is my second year working on the AUVSI project and my third year working with UAS Technologies. My role on the team is making sure the hardware and software systems are integrated correctly and perform accordingly. On the flight line, I will be communicating between the safety pilot and GCS and ensuring the hardware and software systems are operational.
My name is Christopher Hamilton, and I am a third year aerospace engineering major. This is my third year working on the AUVSI project and my third year working with UAS Technologies. I am the hardware team lead, and my role on the team is to oversee the development of the UAS and payload. My job on the flight line is to assemble and prepare both the UAS and payload for mission demonstration.
My name is Kai Gerner, and I am a second year mechanical engineering major. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is constructing the UGV payload, and on the flight line I will be assembling and preparing the ground vehicle.
My name is Patrick Quach. I am a second year aerospace engineering major. This is my first year working with the AUVSI project and my first year working with UAS Technologies. My role on the team is to incorporate interop communications into our system and integrate software subsystems with Mission Planner. My job on the flight line is to operate and monitor the ground control station.
My name is Austin Nguyen, and I am a first year electrical engineering major. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is to develop software for the UGV, and my job on the flight line will be to prepare the UGV for the mission.
My name is Andrew Moffett. I'm a second year aerospace engineering major. This is my second year working on the AUVSI project and my second year working with UAS Technologies. I'm software team lead, and my role on the team is to ensure all software is integrated and developed correctly. My job on the flight line is to monitor and maintain the ground control station.
My name is Tristan Sherman. I'm an aerospace engineering major. This is my second year working on the AUVSI project team and my fifth year working with UAS Technologies. My role on the team and on the flight line will be safety pilot.
The UAS is a twin-motor V-tail aircraft with custom-fitted landing gear. It is composed of mainly styrofoam with wooden supports. Two 4,500 mAh 6-cell batteries power two prop-drive V2 electric motors. Both motors have tri-blade 13-inch propellers with a pitch of 8 inches. The UAS also uses one 3-cell battery to power the flight controller and one to power all servos. The UAS utilizes the Pixoc 2.1 flight controller, which receives its commands from Mission Planner software at the ground station. It is also outfitted with a Sony Nex 7 digital camera used in image detection.
We will be attempting autonomous flight, obstacle avoidance, object classification, and airdrop. We will not be attempting off-axis and emergent target detection. After extensive testing, we are confident in being able to accomplish autonomous flight with a determined waypoint accuracy of less than 15 feet. Obstacle avoidance has demonstrated a consistent ability to evade objects with a radius as large as 50 feet, giving us a high confidence even for more complex scenarios. Object detection and classification uses a neural network and has been extensively resolution tested. From these tests, we are confident in being able to detect and classify objects at around a 90% success rate.
We have had a total of 7 successful autonomous flights and additional UGV independent missions. Due to the need for a manual takeoff and landing, the average amount of time we spend in manual mode is about a minute. We are tuning auto takeoff and landing, so we expect to have no time spent in manual mode for the competition. To prepare for an autonomous flight, we first calibrate the gyroscope, accelerometer, and compass for the plane through Mission Planner. We then test the RC inputs and plane servo responses along with the plane's flight modes like stabilize and manual. We also pre-flight calibrate the pitot tube and LiDAR, receive information from the interop server, upload the mission parameters to the Pixoc through various buttons, and set the plane into auto mode when we place it on the runway. It takes off, executes the mission, and we activate the drop portion of the mission using real-time wind data with a button, and then it auto lands on the runway. Because of this year's large plane and large turning radius, the waypoint accuracy is about 15 feet from the desired location. Over the course of our flight tests, we attempted roughly 30 waypoints. we hit approximately 25 waypoints, giving us a 20% miss error.
Obstacle avoidance works primarily on Dijkstra's algorithm. Nodes are established a certain distance from every obstacle, and possible paths are drawn between each node such that the path does not collide with an obstacle or travels outside the boundary area. This is mathematically obtained by representing the possible path as a line segment, each obstacle as a circle, and each boundary as a line segment in 2D space. Dijkstra's algorithm then begins by calculating the most efficient path to each node, working from start to goal. Once the most efficient path to the goal has been calculated, the algorithm outputs the path as a set of intermediate 2D waypoints. GPS coordinates are transferred to a model 2D plane and, after calculations are completed, transferred back to GPS coordinates. The obstacle avoidance code does assume a flat flight field with ideal conditions. So far, obstacle avoidance has worked with a 100% success rate. Every test conducted has passed, ranging from simple to complex. In the case of one obstacle blocking the path between two waypoints, a simple avoidance path was successfully generated in the most efficient manner. In more complex scenarios with a large number of obstacles between multiple waypoints, the path generated is always successful and efficient. This was tested with the number of obstacles reaching 10 and the radius of each up to 50 feet.
The tests conducted on the imaging system were resolution tests, done during flight to ensure that the resolution of the objects were high enough to be identified by the neural network later. These tests included weather conditions, altitude in flight, hidden objects, and the structural safety of the mount. The resolution selected for the camera is 6000 by 4000, which outputs the objects having a resolution of around 128 by 128 after cropping. The camera will take around 500 pictures throughout the entire flight. Some statistics of the Sony Nex7 camera are 24.3 megapixels, an 18mm focal length, and the camera was tested at distances of 100 feet or greater. In order to achieve the best image quality to feed into the neural network, the test images were created using various weather conditions to ensure that the network could identify the objects no matter their surrounding environment. The autonomous detection was tested using the database of test images generated for training the classification neural network. By using targets in similar colored environments, the detection algorithm is able to identify targets even if they are the same color as their background. The classification neural network was tested using the outputs of the autonomous detection, as well as it was tested using falsified outputs of the autonomous detection. This ensured that the classification network can detect false images and not run a full analysis on an image with no object in it. The network was trained on a set of simulated objects, but all of the testing of both networks was done on real objects, created by hand, and put in real environments to test. The accuracy of both networks is above 95%, with the autonomous detection being around 99% accurate and the classification being around 97% accurate. The localization algorithm was tested both in flight and with images given a GPS coordinate. This was done due to enable testing of the system without the need of an actual flight test, and it proved to help increase the accuracy of the localization during the flight test. The algorithm was tested on the same number of objects the detection algorithm was tested on, as well as it being tested on some of the simulated objects used to test the classification network. The average error in the localization code is around 5 feet, which is acceptable for our uses.
A test payload with a weight similar to the UGV was created to test the drop code. The pitot tube, along with Mission Planner, would record the wind speed and direction throughout the mission. It would then relay the data to the MATLAB code that would sort it for appropriate max wind speed values and heading, then calculate the necessary drop location. Drop was attempted at the end of each mission, and the distance between the desired drop location and actual drop location was measured to determine accuracy. Airdrop has been attempted 7 times, and the parachute has successfully deployed every single time, with a typical duration of 14 to 16 seconds.
Our flight tests have been used to test subsystems individually and general flight characteristics of the aircraft. In initial testing, no mission tasks were attempted as we only gathered data on turning radius and flight parameters for auto takeoff and landing. We then moved to testing obstacle avoidance, which takes a complete mission and obstacle positions to make a replacement mission to evade the objects. So far, the program has demonstrated its ability to avoid all obstacles. Additionally, we used these flight tests to gather data for the pitot tube to extrapolate wind direction and magnitude for airdrop calculations. Finally, we tested the airdrop mechanism by setting different drop points. The aircraft has been able to successfully deploy the UGV with no complications, giving us a high confidence in the airdrop subsystem. The biggest issue revealed by the flight test is the large turning radius of the craft. Due to a heavy payload and fixed wing design, we found that tight turns were forcing our aircraft to overshoot. We are correcting these issues by incorporating the turning radius into obstacle avoidance and survey pathing for image recognition. There were two other major flaws in the system. One was the inability to have the camera take photos or video while connected to an onboard computer because the camera would be in a mode called USB mass storage. We will be doing the image processing on the ground to remedy this issue. Secondly, the aircraft would take 800 feet while at 100% throttle to take off. The twin motors with an 11-inch diameter and a 4.5-inch pitch propeller and a 4-cell battery did not provide enough thrust, and we observed it to be very sluggish.
The types of developmental testing we conducted were subcomponent testing and full mission testing. Initially, we individually tested our components in isolated environments. For example, obstacle avoidance, we tested the program with simulated obstacles to verify that the UAV won't try to avoid them with maneuvers that are impossible for a fixed-wing aircraft to perform. Other tests included payload drop. In this step, we made sure that the mechanism will function properly during the flight and that the parachute will deploy correctly. In conducting these developmental tests, we were able to isolate and fix any issues with subcomponents more effectively. After we verified that there were no issues with the individual components, we proceeded with integrating the subcomponents into the system. At this point, we conducted full mission tests to pinpoint any problems or conflicts between components and the system as a whole.
The max percentage points achieved from all missions was 96.8%. We are unable to do off-axis target and emergent target and are not yet confident with our capability to do autonomous landing. The score we expect to receive is 92%. This comes from the possibility of dropping off by more than 30 feet, waypoint navigation off by 15 feet, and geolocation off by more than 7 feet.